All right, welcome everyone to the next lesson in this series, and today we will look at Kubernetes services. Now, hopefully you have a basic understanding of the constructs in Kubernetes. For example, for workloads, we have constructs such as deployments, stateful sets, daemon sets, cron jobs, etc. And similarly, for networking, there are some constructs as well, namely services. And under services, there are different type of services. For example, ClusterIP services, headless services, node port services, load balancer type services. Okay. Now, in today's video, we're going to look at cluster IP services, and we will look at the other type of services in subsequent lessons. So to start off, why do we need services in Kubernetes? Now, in the previous lesson, we were looking at pod-to-pod routing, and we were testing pod-to-pod communication using IP addresses. Now, in actual Kubernetes deployments, IP addresses don't hold a lot of weight. They are not associated with a particular workload or a service, and they're not bound to any type of workload identity. And that's because IPs are dynamic. They are ephemeral. They are configured on a pod as and when pods are deployed in the cluster, and they're not deterministic. Okay. So for workloads in the cluster, there needs to be a mechanism by which they can discover other services, because in a microservices architecture, which is often the case when workloads are deployed in Kubernetes, services, even within a single application, have to be able to seamlessly discover and communicate with their peers. Okay. So for this, there's a construct known as services, and cluster IP services are used so that workloads inside the cluster can seamlessly discover peer services and communicate with them. Now, in this video, we will look at how cluster IP services work under the hood so that you have a good understanding of troubleshooting issues that could arise when workloads are trying to communicate with other workloads in the cluster. Okay, so let's start with a diagram as always. So in this diagram, we have a few components. To start off, we have kubeAPI, which is the API server for the Kubernetes cluster. And we also have etcd, which is the data store, and etcd stores the status of the cluster. Okay. Now let's take a scenario where a user configures a service. So that request is sent to the API, and the API persists that object in etcd. Now, when the API receives a request to create a service, it also assigns that service what's known as a service IP. Now, we have to make an important distinction here. In a cluster, you have the service IP range, and you also have what's known as the cluster side or the pod sider. Now, the cluster side is used by the CNI to assign IP addresses to pods in the cluster, and the service side range is used by kubeAPI to assign IP addresses to services in the cluster. Okay. So in this case, when the service is created, before the service state is persisted in etcd, kubeAPI also assigns an IP to that particular service. Now, in your cluster, you're going to have cluster nodes. You may have dozens, if not hundreds of cluster nodes. And in each of the cluster nodes, you have a daemon set known as kubeProxy. Now, the function of kubeProxy is to list or watch certain objects in Kubernetes, in this case, services and endpoint slices, and program the respective IP table rules so that you can facilitate client to destination pod communication via services. And let's look at what that means. So let's take a client pod. I mean, just like any other workloads, it could be your servers, your laptops. When a client wants to communicate with a service, it's going to do a DNS lookup for that service. Okay. So when it does a DNS lookup, so in my case, in this lab, we have a service here called nginx-service. So I'm just going to call this, nginx. And this service is backed by certain pods. Okay. So when the client wants to communicate with this service, it's going to do a DNS lookup for nginx-service and receive an IP address. Now, the IP that it receives in this case is the IP that was assigned to that service when it was created by the Kubernetes API. Okay, so now that this client has the IP address of the service, let's take a scenario where it wants to send a connection to this service. So it's going to formulate a packet that's going to have a destination IP that is the same as the service IP that it received from the DNS lookup. Now this packet, as it traverses through IP tables, is gonna get destination natted to one of the backing pod IPs. Okay. Which one? Well, that is probabilistic. It happens in a round robin fashion. Okay. But for the purposes of this discussion, let's say that it gets natted to the IP of the first pod over here. All right. So this packet initially had a destination IP that belonged to the service IP. It goes through IP table rules and then gets destination natted to a pod IP. So when this pod receives the packet, it's going to see a packet with a source IP of the client pod and a destination IP that belongs to itself. So this pod is then going to process the packet and send a return packet, send a response. Now that response is going to have a source IP which belongs to the destination pod, right? Because this is the return packet, and a destination IP that belongs to the client that initiated the connection. Now, as this packet goes through the NAT table, and there's a bit of a nuance here, I'll come back to that later, right? But as it goes through the NAT tables, it's the initial NAT that was performed is going to get reversed. So this source IP that belongs to the pod is going to become the source IP of the service, and the destination IP will be the same since the traffic is destined to the client pod. Okay. So from the perspective of the client, it's going to see a return packet from the initial destination IP to which it sent the connection, right, as is intended, right? Now, the nuance I was referring to is, as the packet comes back, it's not the IP table rules, but the NAT table in contract that reverses it, right? That's a bit of a nuance, just bear that in mind. But as far as the end-to-end communication is concerned, this client sees packets coming from the IP it sent packets to. And as far as the destination pod is concerned, it thinks that those packets were destined to itself, right? So this is what happens when a client tries to communicate with a service. Now, as this client initiates or other clients initiate more connections to this service, the NAT table rules will ensure that they are equally load balanced to these backing endpoints. Okay. Now, these destination pods, right? So if you look at this client pod, it is in a certain cluster node, but these destination pods could reside in either the same node or any other node in the cluster. That doesn't matter, right? The process is still the same. If they reside in other nodes, this packet will have to traverse the pod network to reach the destination node as well, right? However, the end-to-end process shown here, regardless, remains the same. Okay. All right. So with that understanding, let's look at the lab. Now, if you've cloned the repo in the container lab folder, you're going to find another folder called K8S services, and the files for this lab can be found in this folder. Now, in my case, I've already deployed the lab. We have another video that talks or walks through in detail as to how this lab can be deployed. Now, let's look at the files in this folder. So first of all, I have my container lab topology. Very simple. In this case, we are deploying a kind cluster. Okay. And if I look at the manifest of that cluster, we have a kind cluster, in this case, with default CNI disabled since we're installing Calico CNI. And we have the pod subnet. We looked at this previously, 192.168.0.0.16. And the important thing here for this lab is the service subnet, which is 1096.0.0.16 for this particular lab. This is a very important distinction. The pod subnet is managed by the CNI. It uses it to assign IP addresses. The service subnet by Kube API used to assign IPs to services in the cluster. And make sure that these two subnets do not conflict or do not overlap in your clusters, and preferably not with other environments in your broader network as well. Okay. All right. So in my case, I have already run the deploy script, and as you probably already know, the deploy script spits out the kubeconfig file for this particular cluster as well. Okay, so let's start off very quickly by looking at the container lab topology. I'm going to remove this flag. I seem to have some issue with the -t flag. So with that flag removed, this is what my cluster looks like. It's a 3-node cluster, and these are the IP addresses, of the control plane, worker 1 and worker 2 nodes of this cluster. So next, I'm gonna export the kubeconfig file as an environment variable, and then let's look at the pods in the default namespace. So kubectl get pods -o wide. Now, similar to the previous lab, we still have our multi-tool 1 and multi-tool 2 daemon sets. And in addition to that, we also have a couple of Nginx pods, right? And bear in mind the IP addresses of these Nginx pods. So we got 156.5 and 202.196. We will look at these IPs in a bit more detail as we look at the net rules configured by kubeproxy for the Nginx service, okay? All right, so we looked at the pods. Now we will not be using all of the multi-tool pods, probably one of these pods for testing, but what's important for this lab are the Nginx pods. All right, so next let's look at the Nginx service. So I'm going to do a kubectl get services -n default for the default namespace, and I'm going to grep for Nginx service. So in this case, we have the Nginx service, the service we will be testing. And as you can see, this service has an IP of 1096.204.67. This was the IP assigned by Kube API, and you can see that this IP is within that broader service IP CIDR, right, for the cluster. All right, so we've checked the service, and next what we're going to do is we're going to retrieve the endpoint slicers for that service. So if you look at the endpoint slice is going to have two important things. First, it's going to have the IPs of the backing pods. So as we look at the endpoint slice for Nginx service, the IPs of the backing pods are 156.5 and 202.196, as can be seen in the pod IP outputs we obtained previously, okay? And it's also going to have the port, and the port is based on the definition of that particular service. So for example, if I do kubectl get services -n default Nginx service and just say -o YAML, this is the definition of this service, and you can see that we've configured port 80 as the port we want to expose for this particular service. Right now, services could have multiple ports. We're not going to get into that in this lesson, but just bear in mind that for the purpose of this lab, we're exposing a service using port 80. Okay. Alrighty, so with that, let's go to the next step. So what we're going to do next is we're going to exec into this particular multi-tool pod. So multi-tool 1 pod, which is deployed or scheduled in worker 1 in this cluster. So let me clear this output, and right now I'm going to exec into that multi-tool pod. Okay, so I'm inside the pod, and now I'm going to target that Nginx-service. Okay, so I'm going to do a telnet to that service on port 80, and we see that we were successfully connected, right? So now I am connected to the Nginx pod, so I can do something like get, and I receive an output, okay? So what this essentially means is that communication between the client pod to that destination pod through the service is successful, right? All right, so we telnetted to the IP, or rather the name of the service. If I do a ns lookup, and if I copy the name of the service here, I get an IP address, which is the IP assigned to the service. As you can see, this is the 10.96.204.67 IP. It's the same IP that we saw when we looked up the service IP, okay? All right, so what I'm going to do next is I'm going to exit from this pod, and I'm going to now exec into the worker node where the multi-tool pod was deployed. Now, it doesn't matter which worker node I exec into, because these IP table rules are going to be programmed consistently across all the nodes in the cluster, right? But for the purpose of this lab, I'm going to exec into that worker node. Now, in the worker node, we're going to be looking at how the IP table rules are configured. Now, IP tables is a topic unto itself, right? But for this lab, it's sufficient or adequate if you bear in mind that in IP tables, there are certain tables. For services, we're specifically going to be talking about the NAT table. And inside a table, there are certain chains, and the chains are kind of sequenced or linked up together. So for this lab, there is a chain called the kube-services chain. that chain essentially has the rules for all the services in the cluster, right? Now a packet is going to match a certain rule in that chain, which is then going to go into another chain. It's going to essentially jump into another chain. And we have what's known as a kube-svc chain, which is a chain per service, right? So this is going to be specific to a service. And when a packet matches a certain rule in this chain, it's going to jump into some other chains which are specific to a particular endpoint, a destination pod IP, right? So this is how a packet flows through IP tables, right? Just bear in mind that in the NAT table, there are certain chains, and we're going to look at how the packet traverses these chains before it reaches a certain destination pod, okay? Alrighty, so I'm inside the worker node, and first we're going to look at the kube-services chain, and I'm going to grep for nginx-service. So as I do that, we get this output, and what this output says is if a packet, matches this destination IP, which is the IP of the service, right? So as pods do DNS lookups for that service, they're going to receive this IP and formulate a packet to that destination IP. If it matches this, right, and if it's on port 80, right, jump to this chain, okay? So let us go back to the diagram. So we were looking at this. So if it matches a rule, what it says is jump to the second chain, all right? So next what we're going to do is, based on the name of this chain, we're going to retrieve the output of that second chain. So the second chain here, so this one basically has, if I'm to expand this, a couple of outputs, right? So the first one here is for kube-ceph1, and the second one is, kube-ceph2, which is the second chain. And that's because when we looked at the nginx pod initially, we had 2 pod IPs, and that's why you see 2 endpoint chains, right? So we had the service specific chain, so we retrieve the output of this, and we see 2 endpoint specific chains because we have 2 endpoints for the nginx-service. And as you look at this output, I know this is a bit of a verbose output, but this output over here, it has 2 IPs, 192.168.1565, which is the IP of the first nginx pod, and 202.196, which is the IP of the second nginx pod. So what this output essentially says is when packets match these rules, send 50% of those packets. So if you look at this, it has a statistic mode random probability, 50% to this chain over here, the first endpoint specific chain, and everything else sent to the second endpoint specific chain, right? So that is the probabilistic load balancing of traffic between the 2 endpoints, right? So it's going to get load balance in a round robin fashion, right? So 50% of packets are going to go to this first chain, and 50% of packets are going to go into the second chain. Let's see if I can get a better output over here, right? So as you're looking at this output, there are a few columns. So the target here specifies the target chain, and we have the source and the destination. These columns aren't perfectly aligned, but what this says is, regardless of what the source and destination is, if you come to this chain, which is the service chain, send 50% of packets to this particular chain and 50% of packets to this particular chain over here. So now let's look at the output of the first chain. So I'm going to copy this, right? Let's expand our window over here. So if I look at that output, you're going to see the destination NAT we spoke of, right? So this chain is going to DNAT the traffic, or destination NAT the traffic, to the first pod IP address, right? So destination NAT the traffic to the first pod IP address over here. And similarly, if I retrieve the output of that second chain, and I'm just looking at over here, so this is examine the DNAT for the second endpoint, right? If I retrieve that output, we're going to see that it's going to have a DNAT for the IP address of the second nginx pod, okay? Now, let's look at a diagram that summarizes all of this, right? So I have this diagram over here. Let me expand my window a bit. And I know these outputs are a bit verbose. So first of all, we started with the kube-services chain, and we grepped for nginx-service so that we get the output specifically for the nginx service, right? And just to highlight this a bit, so if I run that output one more time, so instead of grepping for nginx, let me just get the complete output, right? Let me just clear that and do that one more time. So if I get the full output, you're going to see rules for all the services in the cluster. This is a lab cluster, so it is a small set of services, but if you get this output, it's going to have, it could be pretty large depending on the size of your cluster. It's going to have the rules for all the services, right? But we grepped it with nginx-service to specifically get the rule for the nginx service. And what that rule said was, if the packet matches a specific destination IP, which is the service IP of the nginx service, and if it matches port 80, jump to this chain. So when we came to that chain and looked at the output of it, we saw two more chains, and those two chains correspond with the two endpoint IPs, the two nginx pods, and it's going to send 50% of the traffic to one chain and 50% of it to the other chain. And in the respective endpoint chains, we saw the DNAT. And this DNAT is what basically destination nats the traffic from the service IP to the destination pod client IP. So going back to the original diagram, it's that DNAT that changes this IP from the cluster IP to the destination IP of one of the target pods. Okay, so if I know the outputs here in my screen were a little verbose, but if you go through the lab guide, right, and I have provided a diagram here that simplifies some of these outputs as well, but the lab guide clearly outlines, how we went from one service to another to determine how a given cluster IP is destination netted to a pod IP. Okay, now I know this was a lot of information. You're probably wondering why you should know all the inner workings of how packets are forwarded in Kubernetes. And trust me, I've been in many scenarios where we've had to troubleshoot issues with services, and knowing how they are configured under the hood really helps in that process. So step by step, first of all, looking at what the service IP is for a given service and then mapping that to ensure that all the endpoint IPs are correctly reflected with the right ports. And if needed, based on certain scenarios, you might even have to go to the node and troubleshoot what happens under the hood. Okay, so before we close, I want to say that Calico also has another deployment option where Calico can replace the functionality provided by kubeproxy, and that is available in Calico's eBPF data plane. We will explore that in one of the subsequent lessons, right? But having this foundational understanding of what kubeproxy performs is, I would say, very important towards understanding how packets are routed and forwarded in a Kubernetes cluster. Okay, so I hope you found this useful. Thanks for watching. I'll see you in the next one. Have a good rest of the day. Bye for now.